Hey everyone, I want to thank you for tuning in to one of ePartrade's Race Industry Now Tech webinars. If you're a part of the racing industry or you're just passionate about racing tech, don't forget to like this video and subscribe to our channel so you never miss a new episode.
Good morning and welcome to Race Industry Now, the weekly webinar series from ePartrade, presented to you by ARP, Performance Plus Global Logistics, Feria, PIC, Fifth Third Bank Motorsport, Quire, and CTEC Manufacturing. I am Francisque Savignan, the founder and CEO of ePartrade, the racing industry, every minute, every day. This is episode 549, and we're going to be talking with MEC CNC. Our host, Mr. Brad Gilly, unfortunately had a last-minute emergency, so can't be with us today, so I will be hosting. With me this morning is Judy King, the co-founder of ePartrade. Judy?
Thank you, Francisque, and thank you everyone for joining today. When I think about today with Anthony Usher and Chuck Lynch, I'm thinking that we have two industry powerhouses. Not only that, we're going to learn CNC machines with MEC CNC. So we're delighted to have them on. Here comes Anthony, and we're going to have Chuck here in a moment too. Francisque?
Absolutely. Thank you. So this is episode 549. It's called Advancing Performance Modern Machining Method for Cylinder Heads, presented by MEC CNC. And it's featuring Anthony Usher, who's on screen with us this morning, who's the president of MEC CNC. And any second, we're going to welcome Chuck Lynch, who's the vice president of technical services for the AERA, the Automotive Engine Rebuilder Association. Good morning, Anthony.
Good morning. Hi, Francisco. Hi, Judy.
Good morning, Anthony. And I think we've got Chuck joining us any second. So we'll welcome Chuck with us any second. And again, apologies, Brad Gilly, who usually hosting these webinars, couldn't be with us today. So good morning, Chuck.
Good morning.
How are we doing today?
Doing great.
Excellent. So I believe you guys are very prepared and have a PowerPoint to share, Anthony, right? Why don't we just dive into it?
Sure, let me get that going.
In the meantime, if you have any questions, please put your question through the chat and we'll address the question and we'll ask the question to Anthony and Chuck. So, Anthony, on to you.
Well, good morning, everyone. Thanks for joining. Thanks for hosting this webinar. I've been involved in the engine machining industry for, well, over 4 decades and been involved with using machines in my own shops and designing and developing machines for the industry. And I'm very excited to be bringing some information about cylinder head machining and some impertinent information that's very important. And glad to have Chuck on board with us. Chuck has immense knowledge about engine machining and things like that. So we'll get straight into this and let's get going. And Chuck, I think you, someone that knows a lot about valve guides, and perhaps you want to get things shooted off with a little bit of explanation about the valve guide.
Absolutely. So, as the title states there, where it begins. So we always have to have a datum point for anything that we're machining, correct? And it cannot be more important to the longevity of the valve seat that the valve guide actually control that. And so, you can't produce accurate valve seats if you don't have a very, very accurate guide to begin with. It's the reference point. So many times in machining, we look at maybe head gasket locating dowels, the dowel pin that locates the transmission. There always has to be a reference point. The crankshaft center line is super important to the block. But when we think about the, valve being able to seal combustion, we have to have that great reference point of the valve guide. So remember, the guide is the guide, not the seat. So that's where we sometimes falter in our machining practices. So we don't spend enough effort on making a good guide. So we go and cut the seat. The machines will cut the seat, but it just won't be the reference that we need. And then we can have excessive runout and so forth. So when machining the guide bore should be finished without any any tearing of material, so which means good tools. You do not want out of round or taper. The desired methods to finish the guide is honing, and they're because reamers can just kind of follow the path that they're given. So of course you bore or ream initially, and then you can do the really close tolerance finishing. So in all machining, and I'll refer to say crankshafts or camshafts, or we rough grind and then we finish grind, then we polish or lap. And that's kind of what you're doing here when you're looking at the valve guide if you do a finish home. So it's just truing up the surfaces. And again, that is true of like a crankshaft housing bores and so forth. There are hand tools and machines that can finish home guides to an accurate diameter and surface finish. And Anthony can definitely speak to that because that's something that they've put a ton of effort on in the past few years.
Yeah, we at Robbins, we've been working on developing valve guide finishing machines for quite a few years now. And we have a number of machines out in the marketplace, different types of engine builders using them. And this particular machine shown in this picture is able to do all the different kind of valve guide work. Some people are oversizing existing valve guides, 4 or 6 or 8 thou. Some heads don't have removable valve guides, so this machine is able to core drill out the parent material so that valve guides can be installed. And then, of course, the final process of honing the valve guide is done as well. We have some users of this machine who's starting to use cross-hatch finishing inside the bore of the valve guides. And we're hearing people are able to reduce the clearance between the valve stem and the valve guide because they're able to not only control the diameter of the valve guide, but also the surface finish of the valve guide. And the less clearance between the valve stem and the valve guide, the better valve control and the better performance, and of course, the longevity of the valve guide and the valve stem.
Yeah, absolutely, because straightness is paramount. And so I know that you've done a lot of presentations on cylinder bores, and we talk about measuring cylindricity. A bore gauge is a 2-point method. I can measure diameter and stuff, but I could never truly measure if that guide was banana shaped. And that's one of the things that is quite the conflict when you do just reaming, is that you can produce banana shaped holes. So you can imagine if it's a banana shape and I have a big long valve stem that's going through, there are going to be points of contact. So how do I get rid of those points of contact? We usually make them bigger. But if we make them true, straight, round, we don't have to run bigger clearances to accommodate things of that nature. So yeah, there's a huge opportunity to improve the guide sizes, clearances, and again, that datum point that we were talking about earlier by honing the guides.
Okay, well, let's go on and talk about the valve seat and some of the details on what goes on in the valve seat. And Chuck, would you like to take this?
Sure thing. So the purpose of the valve seat is combustion seal. So in an opportunity to take advantage of that, in the performance world, they have some very, very high seat angles. So 55 degrees. What that does is increase the wedging opportunity of the valve to the seat. So that's going to increase the opportunity to make a seal, a very fine line contact. But the downside to that is the valve can actually want to kind of stick in the seat if the materials aren't matched. But again, that's very, very common in the performance world. Secondly, or you want to transfer the heat from the valve head into the casting. So going back to that guide, that's going to help you control the valve seat runout or concentricity. That is going to be paramount in that transfer of heat. High temperatures can be helped by having like water flowing around the valve seat area. In that illustration, you'll see like the red arrow is showing that would be like a water jacket behind the seat. So as coolant flows around that area, it exchanges heat with your cooling system. So it's, very important that you have good seat to valve contact, just as you should have very good ring to bore contact, because an engine is quite the experiment of thermodynamics, right? So every uh, part that's getting hot has to exchange heat with another part. So the valve seat,
Chuck, we've got a little question, if you don't mind, if you can address it.
sure.
What about triple angle valve seats?
Okay, so that's one of the things that it's about flow, about the breathing around the valve. Actually, that the picture that is showing up on the screen now kind of indicates the valve seating area. So that's where the valve seat is going to contact just against the valve is usually the angle that we talk, that's a 45 or the 30 or whatever. The other angles are more about flow. So the airflow into the combustion chamber. So there's a lot of different recipes depending on the type of engine, the the duty the engine's going to see, what service it's in. But many times, three angles is just a small part of it. We often have five, seven angles. Um, and when we go back and rework some of the OE stuff, we'll modify that. So again, we can end up with many more angles, but that's more about airflow around it. Now you can also do things and Andy will get to this later because that was one of the slides that we do have ahead is also multiple angles on the valve itself. So typically we're talking about the valve seat and multiple angles, but there are multiple angles ground into valves for some applications.
Excellent. Thank you.
So this is something that's in my career, and I've been doing this for 30 plus years as well. Um, but trying to move to a non-interference angle, and it's absolutely impractical because we're relying on a valve manufacturer, we're relying on insert cutting bits or the tooling. There's just a stack up of too many tolerances. So it's proven that a half to a 1 degree interference angle um, has is the best option. And if you take a look at that top right picture, what you're going to see is the valve seat has got a slightly different angle than the valve. Again, usually a half to 1 degree of interference. That also creates a very fine line of contact, which makes it much easier for the valve to seal as well. So again, when you take the stack up of tolerances, and then it's much easier to seal a very fine edge than a big wide edge. Um, see, form tools, they're usually plus or minus a quarter of a degree on tolerance for manufacturing. And the valve itself has usually got plus or minus a quarter of a degree, so or 15 minutes, which I have spelled out in the slide. And so that just makes it impossible to do, a full contact angle. Also, combustion forces will be applied against that valve head surface area, and it wants to push the valve through the seat anyway. So we often we use the term tuliping of valves, and that's those forces that cause that. What it does is the applied pressure will push on the head of the valve and try to shove it through the seat, and it'll end up getting a cup shape like a champagne flute. So they call it tuliping the valve. So those forces also will do away with some of that interference angle. And what you never want to happen is what we say bottom line contact. I know it's a little hard to see in my image here, but if it's closer to the stem diameter, that would be bottom line. We don't want the angles to go that direction. And it's also true with like piston rings. They can have sealability issues for angular difference as well. So it's very important that we pay attention to angles in a lot of places in the engine, actually. But seat and guides is where it's most recognized. Then you go to the next slide. Yeah. And Anthony, you want to speak about that, or I can?
Yeah, yeah. Well, valve seat runout, which is a very contentious thing, and a few further on the presentation, we'll talk about how to measure it. But this drawing in the top left corner really shows what happens when you have valve seat runout. First of all, the valve is going to contact at one area on the side of the valve seat, which is going to put a bending moment on the valve. And secondly, it's going to push on the valve guide. So you're going to get bell mouth wearing on the valve guide. And one of the most probable causes of valve head breakage is valve seat runout. I have experienced many people who have broken valves or dropped valves, and they immediately blame the quality of the valve and they accuse the valve manufacturer of producing a poor quality valve. But 9 times out of 10, when you start measuring seat runout, you find out the seat runout's the problem, and that's what causes the valve to actually break off.
Absolutely. And that changes with the distance from the valve seat to the guide. So if you have more area between the valve seat and the valve guide, it can be tougher to machine the valve seat, and that translates into eccentricity or valve seat runout. And as Anthony was saying, then you have the issue with the loading of the guide and breaking the valve heads off. And modern valves, sometimes are very long for the performance. So you can only imagine a little deflection at the valve head. What does that mean out here?
Yeah.
That angular, but the thing is, it's captured. The guide's in its way, so it can't move the tip of the valve. So you really need to think about what's happening right here and what it's trying to do here, and the guide's in the middle. So it can't do that. So that illustration is perfect. And if anybody wants the slideshow afterwards, just reach out to us and we can
Sure.
share these images because they're very, very descriptive of what's going on.
And here's some equipment. Chuck, you're so good at this. Why don't you explain these two ways of measuring valve seats and why they're both important together?
Okay, and I usually, as I share this, a lot of folks are familiar with the Stephen Covey's 7 habits, and one of those was synergy. And oftentimes one process is great, but you can take two processes and put them together and they're exceptional, right? So that 1 and 1 can equal 3. And I think that's what used to be, referenced in that old training manual. But anyway, if you take a look at why to vacuum test and measure runout. So vacuum test is a good way to check machine, um, or the assembly arm condition. But like the runout or the concentricity gauge, which you see, the top right, they can tell you things like if I have a machine that's out of level, they can tell you, if I have pilot size selection problems and things of that nature, but they may not catch the like chatter and undulation of the valve seats. Vacuum will not catch valve head deflection if you have nice uniform runout. So the machine cuts without any high frequency disturbances like chatter, then they vacuum test just fine. And I can have like 7 thousandths runout. Again, it goes back to what we were talking about earlier, where we can flex the valve head to the seat. But what runout cannot capture is like a nick on the valve, debris, things of that nature. And what's really happening is the valve's not touching the seat. Well, that one little nick, that's just a tiny little nick on the valve head, but it's actually holding the whole valve off of the seat. So those vacuum tests very well, and you catch that. guide size and geometry can make it difficult, with the pilot selection. So again, it goes back to the how we started this presentation out. Guide size is paramount in importance. So it makes us look in the right areas for the true problems. But the valve seat runout, kind of a good rule is you should never allow your valve seat runout or concentricity to exceed what your stem to guide clearance specification is. So there used to be kind of the rule 1/1000th per inch of valve head diameter. Well, what's the valve head diameter got to do with it? That's irrelevant. It's stem to guide clearance, because if going back to the shape of that seat and the valve contacting one another, it's a wedge. So I'm going to say that my finger, is the valve seat. I'm trying to take two cone-shaped items and jam them together. So again, with that pressure, I can flex, with the springs and the vacuum force, and they can be disguised. So again, 1 + 1 can equal 3. So the correct pilot for measuring valve seat runout. Here is an example that Anthony's got to share with us. But if you see, that's actually got a straight area down toward the bottom of the pilot, and then there's a little bit of taper at the top. So it's 4/10 of a thou, less than a half a thousandth variation in that taper. But what that does is it locks that pilot in a guide. It makes it much easier to check the valve seat run out. Anthony, you want to speak to that some more?
So I had a little glitch with my computer. Can you hear me okay?
Yeah, we can hear you fine.
Okay.
We
Yeah.
can't see you, Anthony. We can hear you, but we can't see you. So okay,
Can,
keep going. It's okay.
oh, you can't see?
Yeah, we can't see you anymore. But we can see your screen, so you're fine. Keep going.
Okay, good. Sorry, something happened. Okay, so measuring seat run out. The pilot is a critical part of measuring seat run out. And we have two basic designs of pilot. One is commonly called a live pilot, and the other one is called a fixed pilot. And a live pilot is floating up and down in the valve guide, and measuring run out with a live pilot is very difficult. So we always recommend a fixed pilot, where there's a drawing of the pilot below there. The part of the section of the pilot that's inserted into the valve guide is straight, and we recommend less than 4/10 clearance between the pilot and the guide in the parallel part of the pilot that's going into the guide. And then the center part of that pilot has a very slight taper, and that taper fixes the pilot into the guide so that the pilot does not move up and down when the concentricity instrument is moving around the seat. The other advantage of this system is that gradual taper in the center of the pilot can also eliminate some of that 4/10 clearance between the pilot and the guide and centralize the pilot in the center line of the guide. So that's a critical part of measuring seat run out. Okay. Sorry, have you can you still see the presentation?
Absolutely.
Yes. So
Absolutely.
yes.
Okay, so we'll get on to valve seat machining challenges. And Chuck, would you like to run with this screen?
Sure. So when it comes to using the form tools, because some people are still grinding valves and valve seats, with the traditional methods with the grinding wheel. But when we talk about the valve seat machining challenges, poor cutting, insert sharpening can produce poor seat quality. And what they tend to do is actually kind of chip and fracture. So you get what looks like lines that are in the seat. Well, if we think about how hard that valve seat is, I'm trying to create a seat width that's, say, 1.5 millimeter or 60 thousandths wide. But if I have chips in the cut, I have that raised material, I might be only contacting the valve against an area that's, say, uh, a quarter of a millimeter or half a millimeter, so uh, 10 to 20 thousandths wide. So you have to really consider that and look at the condition of the seed after the machining. Some of the materials are typically high nickel material. It can, if anyone's ever turned that stuff in the lathe, you know how stringy it can get. And it's also acts the same when you're trying to cut valve seats. So it balls up against our form tools, the cuttings will stick to the insert, and then you start to lose geometry. So that's a bad thing. You want to use the most rigid tooling available and do not extend the tool holders beyond a max radius dimension. So a lot of times folks will, well, I don't really have the tooling that I need to do this next biggest size seat, so I'll just extend that thing out you start to lose rigidity. And that's where you start to get chatter and deflection. And that's not going to end up as a good valve seat. So it may vacuum test fine, but ultimately it doesn't transfer heat well, and you're going to have failures.
So for Robbins machines, we represent a line of machines for various different applications, very small cylinder heads, single cylinder, motorcycle cylinder heads, and various applications of production machining. This particular machine shown in the picture here is a high production machine. It's able to machine valve seats in just a couple of seconds. It's programmable and cuts the seats automatically. And again, the most critical thing of the whole seat cutting process are the carbide centralizing pilots. These photos here is a new design of tooling. Most seat cutting tooling has a single insert, which creates a side thrust. This new tooling system has two 180-degree opposed inserts, and that reduces any side loads and substantially helps reduce seat runout and, of course, any wear in the tooling system. And we have a few customers now using this tooling and obtaining extremely accurate results in seat runout and, of course, surface finish. The other thing that is a common problem is actually setting the diameter of the valve seat that's got to be cut in the cylinder head. Traditionally, a valve seat is a certain dimension smaller than the valve head diameter, and all Robbins valve seat cutting inserts have this dimension that's highlighted in green. We call it the F1 dimension, and you'll see the highlighting there is the distance from the edge of the cutting insert to the top edge of the valve seat. So we take that dimension and we add it into the setting on this fixture, and then we radially adjust the diameter of the cutting insert so we can cut a valve seat to an exact diameter in the cylinder head. Most people at the moment are using a pointer, or they're just literally eyeballing the seat in the head. This method now, you can actually predetermine the exact diameter that the valve seat will be when it's cut in the cylinder head.
Yeah, that's a great tool to help as you get older and you can't see as well. You just set it to a dimension rather than try to, eyeball that. So,
yeah. And then at Robbins, we make the highly developed carbide that goes through quite a few processes of heat treatment, cryogenic heat treatment, and surface hardening. And these inserts are proving to give extended life with very good surface finish. And we have a lot of manufacturers who are switching to these inserts and finding much better results on vacuum sealing and surface finish.
Yeah, and I see that we had a question come in regarding that. So that's actually good timing
Yes.
there.
I was going to mention that. So we actually have two questions. I wanted to know if you prefer to finish the presentation and address the questions after, or we can address those two now if you want.
Let's have a question.
Okay, so the last one, would a 3 bit cutter works more efficiently?
So what was that question, Franz? Didn't quite understand that.
Instead of having two inserts, Anthony, would three work more efficiently?
I don't know of three. I think with the small size of valves, it'd be very difficult to accommodate three inserts. This tooling system is fully adjustable for different diameters, and I think it would be very difficult to make three inserts with any adjustment on it. I have seen in manufacturing situations where they're pre-manufactured cutter heads with three inserts. But our system has to be universal, so we can machine valve seats from 3/4 of an inch up to 3.5 inches, and we need adjustability for different diameters and different size valve seats.
Right. That's what I was going to mention as well, because a couple of projects I've been involved with where it's dedicated to one seat size.
Yeah. Okay, let's go on to the actual valve itself and some finishing there and the different angles in the valve that Chuck mentioned earlier. Chuck, would you like to go ahead?
Sure. So the valve seat part of the valve should be finished to accurate surface finish and a minimum run out. Again, manufacturing, they have specs and tolerances as well. They tend to shoot for under 2 thousandths. Again, we would like to see, much less than that. Uh, the stem end of the valve should be perpendicular to the valve stem. The tip has to be definitely perpendicular. Different angles can be ground on the valve seat, and this goes to what we were talking about earlier. Not only can you do, three angles or whatever on the seat, you can do a lot of these even on the chamber side. There can be some benefit to delipping, or they used to refer to it as camming the valve. So there's definitely opportunity to do that as well. There's so many different finishings out there that you have to be a little bit cautious. If you're reconditioning something that's OE, say if it's nitrided, so that material's not too deep. So if you go and regrind some of those valves, you may be taking that away. So depending on what your application is, if you're developing racing valves, you're probably not looking at those coatings on the faces. But for engines that we're looking to last at, 250,000 of a miles or longer, they may be nitrided on the face. Well, if I grind that and do some modification of angles, and I'm probably taking the hardness away, then that can actually impact the longevity. The surface roughness can eat into the valve seat, depending on the type of the material that was used. But in most instances, you can regrind those, and those are some options that you can have. So,
Yeah, important to, again, measuring. We offer a very precise instrument that can measure valve runout in 10 thousandths of an inch, and this is a photograph of that instrument. This instrument can also be used to check if there's any runout on the stem, because that can also create some problems. Bent valves, as it were.
right, right. And when you have a high resolution, like on that valve runout tester there, then you can pick up things that, like with your valve grinder, say if I see a high little bleep at a 120 degrees separation, then it's probably something with my chuck that is how it's grabbing the valve. So it can also, it can tell you the condition of that particular valve, but it can also tell you what's going on with your equipment or maybe a supplier of your valves. And most valves, there's some kind of date code or whatever, so you can kind of look and do some troubleshooting if you have a device like this. Another thing you can actually do is it's got that stop at the tip of the valve. You can go beyond the end of the valve, and you can set that like as a gauge length. So if I want to check several valves to see that they're exactly the same from the tip of the valve to that gauge line in the middle of the valve where they would be referenced when you're trying to set up a particular type of cylinder head. If it's very critical that you maintain a certain height, you can actually do some of that on this bench, and then that will tell you whether I have variation in my valve seat or is it in the valve.
Again, valve runout, a similar picture we showed earlier, valve runout itself can also create valve head breakage and seat runout.
Absolutely.
This is a machine that we offer, Robbins valve grinding machine. It has a precision chucking system where it holds the valve stem with 6 precision steel balls, and we're able to regrind valves or refinish new valves to within a 10th run out. Well, let's go on to talking about cylinder head gasket surface machining and finishing, and the 3 pertinent factors of this, which is surface roughness, surface flatness, and waviness. We're seeing more and more people requesting these kind of measurements after cylinder heads and cylinder blocks have been machined. And Chuck, I'll hand it over back to you.
Sure. So with modern gaskets, MLS gaskets, they're all stamped steel, so they don't have the soft materials that are accommodating of roughness and waviness that we used to be accustomed to, with conventional style head gaskets. And those gasket types are out there, but by and large, from an OE standpoint and even in high performance, we've moved to MLS gaskets. So can you go ahead and advance, Anthony? Back one.
There.
Yeah. So these are some stylus types. So roughness can be measured with a skidded profilometer. Waviness can only be measured with a skidless profilometer. So if you look at the stylus that actually contacts the surface, that's a really good indicator of what we're looking at as far as skidless versus skidded. The skidless, if you'll back up one slide, you will see the drive unit has to be supported too. It cannot lay on the surface that you're measuring. So the drive unit and the stylus are going to be different to be able to measure waviness. So let's go ahead and advance to why it matters. The flatness is the ability for the gasket to meet the surface, and cold seal materials can only stand up to so much. So if I have a truly out of flat surface, it doesn't matter how much high tack or copper coat or whatever, if combustion gases can squeeze through there, it's going to ultimately blow that stuff out. Now in the drag race world, when you take the stuff apart a lot, you can deal with it. But when it comes to longevity, then you really have to address the issue of waviness. So let's go ahead another slide. Roughness, again, the cold sealability is one of the biggest issues that you're dealing with. We used to want a little bit of grip and bite in the gaskets, but most of the OE stuff now and racing with MLS, you can be really pretty slick. And people will ask, can you be too slick? We won't take enough time to get too slick because you have to do some polishing and lapping, and that's just not going to happen in most of our machine shops. So you don't really have to worry about getting too slick. If you back up that one slide,
All right, Chuck, there we go.
Here, yeah. So that kind of gives you a little bit of an idea of what the gasket would be seeing versus roughness. So all of the up and down little peaks and valleys, is your waviness, or is your roughness, I'm sorry. But if you look at the red line, that's kind of usually what generates waviness is the equipment. It's the rigidity of holding the part. Maybe it's bearings in the machine or something of that nature. So it's a whole different thing than just your cutting insert. go ahead and advance. And kind of remember this. If and Mark Malberg from Digital Metrology shared this. Sorry, I don't see his logo on there. It covered with the formatting of the slide. But so if basically the dimension of your thumbnail or fingernail, if you can see stripes, that's waviness. That's not roughness.
Yes.
So that's very, very important. I've seen a lot of shops where you can see a head laying on a bench and it looks like it's a rainbow. So if that's the situation, you need to look closer and see if you're seeing those indicated stripes, and that's going to be waviness. So you need to make some adjustments to take that out. Impacts of waviness, again, I always say try to think of it as like the suspension bridge. Um, that metal gasket is not going to go down into those areas and fill that void. So now it's like looks like a suspension bridge, and you have a leak path underneath of it. Again, those polymers and what, it may not leak water, but it's ultimately going to leak combustion because combustion forces are too high and they will push that stuff out over time. So factors that can impact your roughness and waviness. PCD works terrific for aluminum, but will fail quickly on iron. So buying the right tooling, it gets expensive, but we definitely should try to use PCD on aluminum because it does work so much better. CBN can work for both cast iron and aluminum, but as I was talking about, some of the high nickel materials will stick to the carbide cutting insert. You will see the same thing. The aluminum will bond itself to the CBN and then it starts to smear. So you lose your edge condition. The choice of edge prep, so you can have dead sharp inserts, you can have lands, A land, T land, a soft hone edge prep, whatever. All of that can impact how your surface finish is as well. The sharper, the better, but your inserts don't last as long. So that's why people will go with things like an edge prep. Machine setup to include level, secure feet, head clamping, the X-axis conditions, your gibs and waves, the drive motors, lead screws and bearings. Just machine condition is super important. And one of the things that we see in the automotive machine stuff is when we mill head surfaces, they're not 100% flat anyway, because we tilt the cutter head so that we don't create a back cutting. If you have an excessive cut, you put a cup in the gasket surface. So usually that spec's going to be 1 to 3 thousandths tilt from over the length of the fly cutter. So if you have beyond 3 thousandths, you're starting to get to the point where you could potentially cause gasket sealing issues. Well, we don't measure long enough with a profilometer to see something like that, even if we were measuring for waviness. So that's something you check on your machines and make sure that you maintain that. And then lastly, spindle speed and feed rate are always going to impact your surface finish or your roughness, because that's the very first thing we're going to do is, okay, if I need a smoother surface finish for my MLS, then I'm going to change my feed rate so I don't advance across the part so quickly. Measuring again, so here's how you isolate the stylus from the part. So this is just an example of a profilometer that has a stand that you can actually bring that device down. You can set the cylinder head or whatever you're working on underneath, and then you can measure that. So it's not influenced by the topography of the part. It's strictly, mapping the surface without, again, being resting on that part.
So just to finish off this section, this is an example of a modern technology surfacing machine. This machine has been developed with specific bearings and spindle design and precision ball screws and thrust bearings so that factors like waviness are very, very small, very accurate. And as Chuck mentioned, the setting up of the cylinder heads. This is a close-up picture of a fixture, and you can see the number of supports and clamps to hold the cylinder head rigidly for machining. Well, that wraps up our presentation, and I'm sure there's some questions. Sorry about the glitch from my side, but at least we got through the presentation with.
Yes, and so first, let's go back to the last question, which is, was the dimension 8 millimeters a few slides back? So what was it?
Yeah, go back. I think that's the waviness
Yes,
is indicated
I believe it
as,
was the 8 millimeters.
yeah, 0.8 millimeters, you know, about
0.8,
30
yeah.
thousandths. So again, that's going to be the, you know, about the thickness of your fingernail. So if you look at that bottom left image, and you start to see like tiger stripes in a frequency of about 30 thousandths in length, 30, 32 thousandths, then they start to be a problem for the gasket to conform to.
So the dimension, Brian, the question is from Brian, it's 0.8 millimeters. We
Yeah.
had a question earlier from Dean Crawford. Which cutters would you suggest for exceptionally hard valve seat inserts?
Which cutters? Are you referring to the cutting insert?
Correct. I think that's because of the, you know, work hardened valve seat. So like your ruby hard inserts, Anthony.
Yes.
Yeah. So that's a good example for those. And, you know, and I've been involved in some folks doing some testing with those as well. And that's exactly why they were requesting those, is because the work hardened seats, they didn't necessarily want to have to extract and replace. As you know, the old saying, iron hardens iron. Well, when an engine's running and that you see those temperatures, sometimes you have a work hardening condition. So I have a valve that's opening and closing many cycles per second and peening against the seat, depending on the materials. Sometimes the seats just get really hard, or sometimes they fail. So it's where are you along that? So sometimes, you know, you can cut through that hardened layer and then get back to, you know, the original hardness of it. Sometimes they've just gone too far. But I think, Anthony, you guys have had some quite good success working with some work hardened seats on like the Duramaxes and so forth, right?
Yes, we're getting very good results with this new Ruby Hard product, and specifically some of the diesel turbo seats, which really work hard. And this new carbide is able to cut those very, very reliably with a long life as well.
Okay, excellent. We're getting close to the end. One last question from Brian. Your slide shows 0.300. Should that be 0.030? I'm thinking we're talking about this question earlier about the 0.8 millimeters that you had the slides.
This slide here?
Yeah. Okay, so.
Correct. That's correct. Yeah.
Okay, excellent. Very good. So I think I see Judy popping up, which signal the end of the webinar. We lost Anthony's video, so good news is we were able to see the presentation, hear his voice, but we can't see you on screen, Anthony. And so I'm sorry, I'm not sure exactly what happened. But fascinating presentation. What so much expertise in there, and I just and thank you from Herman as well. Says enjoy the webinar. So thank you for joining us today. This webinar has been recorded. Will be available later on the Portrait platform and distributed through our newsletter and our social media channels. Don't forget to check MEC CNC's machines and Robin's machines back on the homepage of the Portrait platform. Next webinar will be with Haltech on engine management systems. So once again, thank you and goodbye.
Hey, we want to thank you for watching. Now, be sure to like, subscribe, and click on the bell so you're always up to date with the latest racing technology, industry insights, and exclusive content from ePartrade.